So some housekeeping. The code and like slides will actually be on my GitHub account. To join my other R talk on RServe and fast R web. This talk is somewhat about optimization. So if you want to maximize your contact with me, you can also connect with me on Twitter. And the talk is in 3 parts. The first part is I'm going to talk about this question that was posted on stats.stackexchange. The second part, I'm going to talk about automatic derivatives and why you should use them. And the third bit is actually about the template model builder package that lets you implement automatic derivatives in R. Broadly speaking, I'm going to talk to you about a question that I didn't pose using data I didn't collect. I'm going to reuse some really brilliant analysis from the stats.stackexchange post that I didn't do. I'm going to talk a bit about packages like RCPP that I know next to new about, but now I know a little bit more because of Dirk's excellent tutorial yesterday. But I'm going to add some dubious statistical analysis on top of this. Well, if I'm being kind, I can just say I was being creative, right? So I think that makes me a data scientist. I hope that this talk is entertaining. The reason why I want the talk to be entertaining is that I want you to remember in the future, maybe 6 months or a few years, that when you meet a complex optimization problem in R, you remember that this package called template model builder exists, right? And you don't have to fear this complex log likelihoods. When I first discovered it, I was really, really amazed, and I really wanted to tell people about it, but I had a problem, which was that I didn't have data. Fortuitously, 2 weeks before the abstract submission deadline, someone posted this question about a sequence of ping pong games on stats.stackexchange, and I saw that I could actually use it in the talk. And so here's the question. First, I want to tell you a little bit about the site. This is a very popular question on the site. It's got 85 votes. You can see it on the top left-hand corner. This represents, in terms of percentages, this is in the top 0.1% of questions asked on stats.stackexchange. There's 100,000 questions asked on this webpage, so in a different context, this is in close to the top 100 questions on that site, and this is in the last 4 months. The question goes like this, really. So this guy, his name is Richard. He has bet with his coworker that he's going to beat him in 50 ping pong games in a row. And he's played 15. By the time I got to the data, he had played 21 games. And after 15 games, which he won all of them, he has an average winning rate of 58%. And he's like, can anyone tell me what my chances of making the bet is going to be, right? So win the next 35 games. And conveniently, he's provided us with some data of the first 21 games he played, being the final scoreline in each of these matches. I looked at this and I was like, well, there's an interesting assumption being made here, and namely that the probability of winning a point is constant, right? It's independent and identically distributed across all games. And I wondered, actually, is this true? So if you actually plot the winning margin versus the game number, I see this really strange thing. I feel like sometimes Richard plays really well, but he's won games with a margin of 12 or 13 points. But when he seems to play really well in one game, the next game he seems to tank, right? And after the game he won by 12, he only won the next game by 2. So I was like, well, maybe his rate of winning points is not actually independent between matches, right? There are other reasons to suppose this. I actually think that Richard is a far superior player than his opponent. I don't think, you don't make a bet that you're going to beat someone 50 times in a row unless you're insane or you're really good. And because he posted on stats.stackexchange, we can probably safely rule out insanity. And being the recipient of much charity in office ping pong matches, I know that people, you try and even up the game a bit more so that everyone has fun. So I'll get back to this thing later on about how strong Richard is when I talk about the data generation process. But now I'm going to talk about automatic derivatives. And so we're concerned in the context of optimization. And so as a statistician, well, generally in optimization, you have an objective function. And as statisticians, we are generally interested in log likelihood and decision variables, usually regression coefficients. And so you've got this problem where you want to find the regression coefficients that maximize the log likelihood, right? And there's broadly two ways of doing optimization. You do gradient-based or non-gradient-based. So non-gradient-based is like things like grid search, now the mean, simulated annealing, which we're not concerned about here. I just want to remind you of a very simple gradient-based method that you might have encountered in primary school called Newton's method. And basically, if you want to find the value of x that maximizes the function f, there's this procedure where you start with a guess, x0, and you build better guesses, x1, x2, using the first and second derivatives of the function f. Now you may say, well, what if x is actually a vector regression coefficient? Then the standard trick, right, that everyone says, and it's like, oh, the world is rosy. It's just to replace the first and second derivatives with the gradient and Hessian, right, which are these things. So the gradient produces a vector of m partial derivatives, and the Hessian is a matrix, an m by m matrix, which is like a lot of derivatives to find, right? As an example, to calculate one element of these things, in the standard logistic regression setup, you might say that the log of the odds is a linear function of covariance. And the log likelihood function looks something like this. And then the aim of the game is to differentiate L with respect to the betas. And after some work, you get a really nice expression. But I'm going to leave that as an exercise for you. Right? So that is analytically calculating derivatives or by hand, or the stuff you learn in high school, right? Diff of sine is cos, diff of log of x is 1 over x. At least that's how I learned it. And then when I got to uni, I learned about symbolic differentiation, which is to say, you've got software like Mathematica, you tell Mathematica to differentiate an expression, and you get an answer. And I was like, why did I waste all my time in high school? And then ironically, when I started doing optimization, I learned about numerical derivatives. Right? And this is first principle. So if you want to find this derivative at some value x, you just plug in a very small value for delta x, and you evaluate the expression on the right, and you get an answer. Now, there's two problems. One problem is that if you pick delta x badly, you might run into numerical issues. The other problem is that if f is very expensive to compute, this is going to add some overhead in Newton's algorithm, because you see, you're computing f twice over here. So automatic differentiation is this thing that I discovered last, and it gets around these two problems. Okay, and why should you use it? Well, it is magic. There's minimal additional code or thought that you need to get the derivatives. It's exact. It's just as good as having analytical derivatives. And in the case of template model builder, the cost of evaluating the gradient function is bounded. It's at most 4 times the cost of evaluating the original function. Now, I don't have time to go into more details about automatic differentiation, but this is the blog article that convinced me that I should be using this for the rest of my life. I really recommend that you look at it. Okay, so now we come to the third part of the talk, which is the why, or how you can use TMB to do automatic differentiation. So preliminaries, this is how you install TMB. You go to this wiki, and as of R3.5, it's become really easy. Like it used to take a long time, but now if you follow it, it took 5 or 10 minutes. And there's quite an active support on this Google group. It basically is an R package that lets you supply an objective function in C++. Okay, so this is a little bit complicated. But in exchange, it will give you the first and second derivatives for free using automatic differentiation. And we're going to see that it's very, very fast, and because it uses like state-of-the-art C++ packages under the hood. And you generally use it when you deal with more complex log likelihood functions, right? So for example, there's this package on CRAN called GLMMTMB, and it lets you fit linear and generalized linear mixed models with various extensions, including zero inflation. And if you have a model containing random effects, it also has implemented like Laplace approximation for the likelihood. Right? We're going to see an example of such a complex log likelihood function by going back to Richard, our original poster, who I think is very strong. Basically, I'm going to say that his probability of winning a game, winning a point in the next match is going to depend on his performance in the current match and the final scoreline of the current match, right? So we just let this be the score difference in the ith game. And I'm going to say that this probability is going to be like an average of two probabilities. These are the things in red and green. The rating P0 is what I hope will turn out to be the probability of Richard winning a point when he's not playing well. And I assure you the green thing is a probability. I'm going to explain how it is. So you can see PI, which is how well Richard is performing now. The logic just takes the probability and turns it into a real number. We're going to add some other number to this and then turn it back into a probability using the inverse logic function, which I denote with xfit over there. So alpha is just a ratio between 0 and 1. And it basically just averages between these two probabilities. And the aim is basically to find the value of these four parameters in the equations that maximizes the likelihood of observing the game score lines in the original question. Okay, so this is kind of complicated already. Now, if you know the probability of winning a point, then you can derive the probability of winning a game with a particular scoreline. And there are two cases. One is you win a game with 21 points, then you've got that expression. Otherwise, the game goes into overtime, so you get a deuce at 20 all, and you just keep playing until someone wins with a margin of 2, and then you've got that expression. There's some really beautiful combinatorics that is used to derive these two equations, but I don't have time to go into it, but I can refer you to Wuber's answer on the stack exchange question. Now, the point of this is that these equations are kind of complicated, and to actually get the log likelihood, you need to take the log of one of these things, and then you need to differentiate it with respect to those parameters. Now, the problem here is that the probability of winning a point depends on Richard's past performance. So actually, this is just some easy way of hiding a big nested function for P. And so now the problem for you is that, well, tell me how you differentiate this thing, right? And you're going to see some looks of horror, which is good, which we're going to we're going to bypass that entirely by using TMB now. Okay. So I'm going to show you the R code that implements the objective function. And so you basically see what I've said. You have a for loop that iterates through the sequence of games. And in each game, we blend this baseline probability of Richard playing when he's not playing well with this thing that depends on how well he is currently playing and what the final scoreline is. And for completeness, there's also the probability of observing a scoreline given the point win probability. And now I just want to compare this code to RCPP, where you see that it looks very similar. The only difference in my mind is that when you declare a variable in RCPP, you need to tell R what the type is. And the loop indices start at 0. Because vectors in C++ are 0 index. If you don't start them at 0, your world will end in a sea of indecipherable error messages. TMB code is very similar because it is, after all, C++. The only difference is that you move the parameter declaration into the body of the function. And TMB makes a distinction between two types of data. Firstly, just static data. And the second are the parameters. So if you say something's a parameter, TMB is going to spit out. It will know that it needs to calculate the derivative with respect to that parameter. But otherwise, it's quite similar. So if you already know RCPP, it's quite easy to use TMB. And conversely for me, because I started with TMB, it was fairly easy to pick up RCPP, or at least to start coding badly in RCPP. Okay. It tries to make things easy for you. So the make AD func basically compiles everything, and it returns the R, an object that you can directly use in optimization. It's got the starting parameters, the objective function. It tells R that you want to use a quasi-Newton method with BFGS updates, and so on and so forth. Okay, this is the main result of the talk. and this is why you should use TMB if you ever have a complex problem, is that it's very, very fast. So the base R implementation at the moment on my computer when I ran this is like 30 times slower than RCPP, right? So you can see that in the mean column. TMB numerical is basically just a TMB objective function, but I've just deleted all the automatic stuff, right? So this is to show you that actually TMB is just as fast as RCPP. Well, it's just as efficient as RCPP. But if you add the automatic derivatives, you can get a factor of 4 increase in speed, right? So I think that is actually really good. Like in real life usage, like I had optimization problems that were taking, I was going to bed and waking up and hopeful that nothing crashed overnight. And I could now do these optimizations in like 10 minutes. Like it's really amazing. We can't really do statistical analysis without talking about the regression coefficients. So here they are. It may be a bit more useful if I just sub them back into the equation. And so let's go through what the model fit actually means. So let's look at the rate number. The rate number is 0.546. Now this is a lot lower than 0.59, which is the average rate at which Richard was winning points, right? So I think that when Richard's not playing really well, he actually, he really is not playing very well. Like, when he's tanking, his chances of winning a point actually are, about 55% instead of his average, which was 59%. Now, look at the green stuff. If he wins, if it's a tight game, say the score difference or the winning margin is only 2, then this is the x-fit or the inverse logit of a very negative number, so alpha is close to 0. In this case, what actually happens is that you take his performance in the current game and you add a little bit to it. That's the blue number over there. And that means that in the next game, he's going to play a little bit better than he does in this game if he doesn't win this game by a lot. It might be more useful to just plot the fitted game up. Sorry, there's a typo there, which I meant to correct, but I didn't. The fitted point win probabilities. So the red line is the average win, the average observed win probability, which is 59%. And the green line is the model fitted probability. I hope you can see that the model has said that Richard wins. It should win a lot more points actually when the winning margin. You see, it matches up. Like when he wins with a big winning margin, those were the games that the model thought that he was playing well. And when he doesn't, when it's in a close game, that's when generally the model thought that he was not doing very well. Okay. So in conclusion, I hope that I have demonstrated that TMB is a very useful package and that you should use it whenever you meet a complex problem because it is very, very fast. So that you can actually feel free to explore more interesting log likelihood functions and not restrict yourself to the usual ones. But I think it's fair in a talk where I've borrowed so much from everywhere over the internet that I should leave the last word with Richard, and it concerns whether the points and games are independent, right? And Richard has his reply. He says that I don't think the points and games were independent. The more I won, the more complacent I got, and my opponent took advantage of that. For your information, he lost his bet on game 28. Thank you all for your attention. Yes.
So if alpha equals 1, that means the games are independent of your model.
If alpha equals to 1, then the games are independent. Well, sorry, if alpha equals to 0, you mean? Oh, yeah, sorry, 1. Yeah, sorry, yeah, you're right, you're 1. Yeah, correct. So, well, as I said before, the analysis is somewhat dubious because there's 21 data points. I'm fitting 4 parameters, so you need to have some element of belief that that the data generation process actually works, right? But yes, I mean you're right. If alpha equals to 1, then the games would be independent, and you should see that the rate number is 0.59 because this is a near maximum likelihood estimate, so it should be the empirical mean. But no, I didn't test it, but because of the way I set up the initial parameters, so I started the optimization at 0.59 with 0 for all the other parameters. So at least I knew that if you could get a better result, then it would actually improve on the empirical mean.